The next simplest example of electric field is that due to 2-point charges. Last time we saw that the electric field due to a point charge is given very simply by taking Coulomb's law. So let me recall that here. The electric field of a point charge would be the force felt according to Coulomb's law on a test charge, and that's kqq over r squared, and then you divide it by the test charge q, so that q disappears, and then you put the direction r hat. That's the electric field of a point charge. Now if you have 2-point charges, a plus and a minus of equal magnitude separated by a fixed distance, this is called a dipole. And that's the electric system we're going to study. The fixed distance is usually indicated by the letter little d, so that's going to be d over 2, and that's going to be d over 2. Now let's focus on this dipole for a second, because there are a couple of things I need to tell you about it. So the positive charge and the negative charge are separated by a fixed distance, meaning that the fixed distance is somehow enforced by atomic considerations. Now, typical dipoles like the water molecule is a polar molecule, so the shape of the water molecule is not quite like this. It's more complicated. It's got a hydrogen atom, 2 hydrogen atoms, and an oxygen atom. But the effective shape of the water molecule is that of a dipole. So if you look at the proper chemistry look of the water molecule, it has these 4 valence electrons, and then there's a residual charge, which I'll call delta minus, on the oxygen side due to those valence electrons, and there's another residual charge on these hydrogens, which average to something called delta plus. And delta plus and delta minus are the analog of Q and minus Q. And this distance, d, is given by some averaged bond length distance. So chemists, physical chemists or inorganic chemists will fixate on what appropriate d has to be for the dipole and what the appropriate deltas have to be for the dipole. Now, this is a physics course, so we won't concern ourselves with the details. We'll just assume that these two charges are somehow kept separately from each other. If they're not kept separate from each other, they'll just attract and neutralize, and you'll get nothing. So we have to keep them separate. Let's see what happens when we keep a dipole along the z-axis. Now, there is one important quantity of the dipole that needs to be mentioned, and that's called the dipole moment. The dipole moment is indicated by the symbol P, and it's just a vector that points from the negative charge of the dipole to the positive charge of the dipole. The direction is from negative to positive, and the magnitude of the dipole moment is simply q times d. You take one of the charges, magnitude, and multiply it by the distance. So the units of dipole moment are just going to be Coulomb meters. Coulomb being the unit of charge and meters being the units of distance. So let's just keep that in mind. Let's actually draw it here. Dipole moment vector for this dipole system. Now our aim is to find the electric field at point A and point B. This is actually a nice exercise, because at the end of this exercise you will learn some survival skills. If you are in a area with very poor cell phone receptions, let's say you're in the Adirondacks hiking the 46 peaks, and suddenly you're lost and you find the cell phone coverage is really bad there, this calculation is actually going to probably save your life. So let's see what to do here. Let's join the charges to point A. My first aim is to find the electric field at point A, and then later on I'll do the electric field at point B. I'm also interested in finding out how this field looks at large distances away from the dipole. That's called the asymptotic limit. So I'll write that also. That's my second ambition. The first one is to find the electric fields, and the second one is to examine their large distance behavior. All right, let's start doing this. First, let's draw a picture. At point A, the electric field is going to be in this direction because plus charges push electric field, while negative charges suck in electric field. So the electric field due to the negative charge is going to be like that. And the sum of these two electric field vectors is our resultant. Now if you look at this picture, the resultant is clearly going to be in the negative z direction. The magnitude can be found by simply considering the component. So E cosine thetas will cancel out, E sine thetas will add. So the effective electric field magnitude at point A is just going to be 2 times the electric field of any one charge times sine theta. Later on we'll worry about the vectors, but right now we'll just focus on the magnitudes. For the electric field, we need to focus on this distance, little r. Well, if this distance is x, the distance away from the origin, then that distance r can be found using Pythagorean theorem. So I'll write that here. R squared equals x squared plus d over 2 squared, or d squared over 4. Okay, so now I have the expression here. The electric field of a point charge can be used. So it's 2 times k little q, the capital Q has been taken over by little q here, divided by r squared times sine theta. Now if you look at this triangle, sine theta is opposite over hypotenuse. So that's d over 2 r. So that looks like a pretty nice expression. Now when I see the product q times d, I'll immediately pounce on it and write the dipole moment P instead. So that's going to be k times the dipole moment P divided by r cubed. We are done. That is the electric field magnitude. Now if you want to write it in terms of vectors, what you will do is this. Electric field A would be, if you notice, the electric field is pointing down, but the dipole moment is pointing up. So the best way to fix that is to put a negative sign. And now we are basically done. R cubed, which is going to be x squared plus d squared over 4 to the power 3/2. Don't forget that r itself is the square root of all this. So when you take r cubed, square root is to the power 1/2. So if you take r cubed, you're going to get to the power 3/2. Now for the asymptotics, an easy way to do the asymptotics is the following. If you're going really far away from the dipole, this is rather like watching the two headlights of a car. If you go really far away from a car, the two headlights seem to merge together, and you won't know after a certain distance if you're looking at a car or a motorcycle with just one headlight. So that's really what's happening. The D will be ignored. You can ignore the D, and the electric field at point A, the asymptotic limit, which I'll indicate by this, x going to a very large amount, is going to be negative kp over x cubed. So that's our answer. Let's save that. Now for the other calculation, which is the dipole electric field at an axial point. This is sometimes called the bisector field, because you're on the perpendicular bisector of the dipole. By the way, this field is the same everywhere on the xy plane, because the xy plane is what's bisecting it in 3 dimensions. What about the axial field? The axial field is the field along the axis. So let's find out what EB is going to be. Again, I'll worry about the vectors at the end. EB is going to be the electric field due to the plus charge, which is going to, plus charges put electric field out away from it, and then the minus charge, because it's farther away from the point B, is going to suck pretty weakly. So the net effect is still going to be along the z-axis. So let's put the magnitude of the electric field is going to be K times Q over the distance. Let's call the distance between B and the origin simply Z. So that will be Z minus D over 2 squared minus K times Q divided by Z plus D over 2 squared, because the minus charge is a distance Z plus D over 2 away from point B, whereas the plus charge is Z minus D over 2 distance away from point B. Now this has to be simplified. Let's do that. An easy way to simplify it is to take the common denominator. So that's going to be Z squared minus D squared over 4, the whole thing squared, and the numerator I'm going to get Z plus D over 2 squared minus Z minus D over 2 squared. This can be simplified. You don't have to leave it like that. So I get KQ. The numerator is A plus B squared, so that's A squared plus 2AB. That 2 will cancel out with the D over 2, so that's just going to be ZD plus B squared, which is D squared over 4. And then here I have everything with the minus sign, so just be careful here. That's Z squared minus ZD plus D squared over 4, if I expand the parenthesis keeping the minus sign outside, and that's just going to be Z squared minus D squared over 4, the whole thing squared. All right, now we cancel out terms that have the opposite signs. Now these two will add, because that's a minus of a minus, which is a plus. So I'm going to get K times Q Z D times 2 divided by Z squared minus D squared over 4, the whole thing squared. Once again, I'm going to pounce on this product Q times D. That's just a dipole moment. So that's 2kp Z over Z squared minus D squared over 4, the whole thing squared. I want to vectorize it. Well, this time I notice I don't have to put the negative sign, because the direction of the dipole moment P is the same as the direction of the net electric field. Remember, I told you that the plus wins out, so the net electric field is going to be in the same direction as the dipole moment, so I don't have to do any put any minus signs by hand. So the electric field in vector form, the electric field is going to be EB equals 2kp with the vector sign Z squared minus D squared over 4 squared. Now that's fine and good, but we also want to look at the asymptotics. So let's look at the asymptotics. What happens when Z becomes very big? By the same reasoning as that, you can neglect this D squared over 4 term when you go really far out. So I'm going to end up getting the asymptotic limit. So EB, if Z becomes very large, I always indicate asymptotic limits like this, becomes, and that's also an indication of asymptotics here, 2 times Kp. There's going to, now that D squared over 4 is disappearing, that's going to give me Z to the power 4 down there, Z squared whole squared. Z to the power 4 and Z, so I get Z cubed in the denominator. Right here, you have this amazing result that the asymptotic electric field axial field is twice the magnitude of the bisector field. Now, if you think about radio and broadcasting signals, the intensity is proportional to the square of the electric field. So the intensity is actually going to be 4 times bigger. You're going to get a 4 times better reception axially than if you had a perpendicular bisector. This is why if you have a very bad reception area, the best way to find a good tuning of your favorite AM station is to, let's say you want to listen to WXXI with Evan Dawson or something, then you find the worst reception, that will be your bisector field, and then turn it by 90 degrees, and that will give you the best reception. That will be the axial field. Likewise, if you have a poor coverage in a cell phone area, which is very poor coverage, then if you find very few cell phone bars coming, just turn it by 90 degrees in every direction till you get the best reception.